Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Razin bin Adnan. My matrix number is 088851. Today we are presenting our group project in subject Computer Organization and Architecture. In this video, we will be explaining and simulating about two circuits, which is 4-byte synchronous counter and 4-byte register with load and clear. We will begin with introduction. In this project, we designed and simulated 4-byte synchronous counter, which is sequential circuit. This circuit counts in binary sequence based on clock pulses. It is commonly used to track instruction steps in CPU. Next is 4-byte register with load and clear. It is used to temporarily store data using 4D flip-flops. It has a parallel data storage. Both circuits are essential components and play an important role in CPU. Next, we will be talking about 4-byte synchronous counter. It is also known as logic diagram or Boolean function. It is a synchronous counter that uses flip-flops T or D type all triggered by the same clock signal. Each flip-flop represents 1 byte of the count from Q0 to Q3. The logic for when each flip-flop toggles is based on the AND combination of all lower bytes and enable signal. Each flip-flop toggle change state when its T input equals 1. To count properly, we connect each flip-flop's T input based on lower outputs. The logic equation: firstly, T0 equal enable. Secondly, T1 equal enable AND Q0. T2 equal enable AND Q0 and Q1. And the last one, T3 equal enable AND QO, AND Q1 and Q2. For the next slide shows the simulation design of a 4-byte synchronous counter. The counter counts in binary from 0000 to 1111, which is decimal 0 to 15 using 4 T flip-flops. Because it is synchronous, all flip-flops are triggered at the same time by a single clock signal, ensuring accurate and stable counting. An enable input is used to control when the counter is active, while a reset input clears the counter back to 0000. In terms of components, 4 T flip-flops store each byte of the count. 3 AND gates generate the toggle logic for higher order bits, and one clock input drives the entire circuit. The output are connected to LED or output pins to display the binary count from Q0 to Q3.
Assalamualaikum, my name is Nik Amal Saifi bin Anwar, matric number 088596. On this slide, I will explain the simulation design of the 4-bit synchronous counter. Each flip-flop output labeled Q is connected to logic that determines whether the next flip-flop should toggle or not. The reset signal is used to clear the counter. When reset is activated, all flip-flops are set to 0, restarting the count from 0000. Next, the enable signal acts as control gate. When the enable is high, counting is allowed to occur. When the enable is low, the counter pauses and holds its current value. First, let's look at the control signal flow. The clock signal is distributed to all 4 flip-flops at the same time. This is why the counter is called synchronous, because all flip-flops change their state simultaneously on every clock pulse. Finally, the outputs Q0 to Q3 represent the 4 bits binary count, which is displayed using LEDs or output pins. This slide explains the circuit functionality of the 4-bit synchronous counter. When the reset input is set to 1, all output are reset to 0. When the enable input is set to 1, each clock pulse increases the binary count by 1. Because this is a synchronous counter, all flip-flops toggle together at the same clock edge. The binary output follow a standard counting sequence starting from 000, then 0001, 0010, 0011, 0100, and continuing until 1111. After reaching 1111, the counter resets back to 0000 and the counting cycle repeats. So this is first circuit, which is 4-bit synchronous counter. Now let's simulate this circuit. When I press reset, the output goes to 0. Now I will turn reset off and enable on. Each clock pulse increment the count. We can see it go from 000, 001, 0010, 0011, and so on up to 1111. Then it roll back to 000. If I turn enable off, the counter pause. Turning enable back on, it's continuous counting. So that is for the 4-bit synchronized counter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Faid Haikal bin Shahrul. My metric number is 088766. Today, I want to explain about 4-bit register with load and clear. Logic diagram or Boolean function. 4-bit register with load and clear use the flip-flop that is triggered by the clock and updates its output. Each flip-flop updates its output based on the load signal, clear signal, and clock edge, ensuring data is updated, cleared, or written correctly. This is a truth table of logic equation of this circuit. When load is 1 and D0 is 1, Q0 loads D0. When load is 0 and D0 is 0, Q0 equals to old value. When load is 1 and D0 is 0, Q0 updated new D0. Clear equals to all output Q0, Q1, Q2, and Q3 to 0. Next, simulation design for this circuit. This circuit has 7 components. The first one is D flip-flop. The flip-flop update values when the clock signal changes. Second, multiplexer. Multiplexer choose between loading new data or keeping the current value depending on the load signal. Clock. Clock will synchronize all flip-flops and capture the value from the multiplexers. Load. Load will determine whether to load new data or keeping existing data. Clear. Clear will reset all outputs to 0 immediately when active. Input. Control what data the register stores and when it update or reset. Output. Provide the store data for use in other parts of the circuit. Now, let's look on how to connect this circuit for simulation. Each multiplexer selected either input or the current output of the flip-flop based on load. The flip-flop output connects to the output of its corresponding multiplexers. Clear goes to the reset input of all flip-flops. Clock connects to the clock input of all flip-flops. Steps to simulate this circuit. First, push clear button, then observe all Q0, Q1, Q2 and Q3 become 0. Second, set load equal to 1, enter values D0, D1, D2 and D3, then observe Q0, Q1, Q2 and Q3 will store these values at the next of clock edge. Set load to 0, then observe Q0, Q1, Q2 and Q3 will hold their previous values even if D0, D1, D2 and D3 change. Fourth, toggle the clock to trigger changes. Now we go to circuit functionality. This circuit is functioned as a 4-bit register that stores data using 4D flip-flop, which is FF0, FF1, FF2 and FF3. Each flip-flop stores 1 bit producing outputs Q0, Q1, Q2 and Q3. Multiplexers are used to select either new input data or the current store value. When load is 1, the register loads new data from D0, D1, D2 and D3 on the clock edge. When load is 0, the register holds its previous value. The clock synchronizes all flip-flops so they update at the same time. When clear is 1, all flip-flops are reset and Q0, Q1, Q2 and Q3 become 0. Let's start the simulation for this circuit. This circuit is a 4-bit register built using D flip-flops, which is FF0, FF1, FF2, FF3 and multiplexers. The inputs of this circuit are D0, D1, D2 and D3. Load, clock and clear. First, press the clear button to ensure all outputs are set to 0. Next, set load to 1 and apply values to D0, D1, D2 and D3. When a clock pulse is applied, the outputs Q0, Q1, Q2 and Q3 update to match the input values. Then set load to 0 and change the input data to 0. The outputs do not change and hold their previous values. Finally, set load to 1 again and apply a clock pulse, and the outputs update according to the new input values.
My name is Nur Ainumadia binti Muhammad Azlan. My number matric is 0861084. I will talk about application in real CPU. 4-bit. I will talk about application in real CPU for 4-bit synchronous encounter and 4-bit register with load and clear. My 4-bit synchronous counter, the application in the CPU is control of sequencing and timing, instruction fetch and decode, simple microprocessors, learning CPUs, 4-bit register with load and clear. For the application in the CPUs is control of data storage and reset, temporary data holding, accumulator, instruction fetch and execution, and use in simple microprocessors and learning CPUs. And next, I will talk about challenges for 4-bit synchronous counter. Excitation logic and XOR gates becomes complex with more bits. Requires careful synchronous gating for clear or enable. Challenges for bit register with load and clear. Correct timing between clock, load and clear. Delays in the multiplexers and flip-flops can cause the wrong data to be stored. And the last thing I will talk is the summary. The summary for 4-bit synchronous counter is sequencer in real CPUs, and 4-bit register with load and clear is stores 4-bit data, allows loading new values and clears the data using clock control. In conclusion, 4-bit synchronous counter and 4-bit register with load and clear have to understand how digital systems store and process data. That's all for me. Thank you.